all this small signal model, right? So let's start. We talk about DC bias. Nice. We know how to bias it. From there, we can extract the GM and R out. And then we know how to construct the small signal. And then we can start doing the circuit analysis. On the left is a complicated circuit. If you want to solve it, you need to solve I equal to proportional to VGS minus VT squared, right, which is nonlinear. Now we want to do the small signal. The first thing is what you know very well. The constant voltage source needs to be shorter. That's why this is grounded. The constant current source needs to be open because it's constant. I say that it's constant. The current source always gives me 1 milliampere. So what is the change of the current in small signal? Zero. Because it's constant. No matter what you do to me, I always deliver 1 milliampere. So the change of current is zero. That's why it needs to be open. Means in the small signal, there's no current flowing through. Right? So this is the first thing. You need to do this. Another is to replace the transistor with their small signal, right? So we will do more in the future. This is just a quick overview. First, we identify this is NMOS, this is PMOS, and then use what we have learned. This must be the drain because VDD is on top. This must be the source. This is the source. This is the drain. And then what? Bring in your model. Source is here, drain is here. Same for the PMOS. Source is here, drain is here. And then just connect all of them. Once you have this, KCL and KVL, then you can solve the circuit. You should have learned this before, but this is just a review. Any questions? Now, if not, then we want to discuss a few important quantity definition. We want to define what is R in and what is R out. What is the input impedance of a circuit? What is the output impedance of a circuit? Before that, let's look at the loading effect to see why they are defined in this way. I have an amplifier. It's trying to get the voltage from the previous stage. Right? Just like the teacher is trying to teach you some knowledge. This is the student, this is the teacher. The goal is that I want to get all the voltage from the previous stage. Right? You want to get all the knowledge from the teacher. But you cannot because the teacher has output impedance. The previous stage has output impedance. Just like the teacher does not teach perfectly, they have problem. And you have input impedance, just like you cannot learn perfectly. So as a result, what do you get? You only get V1. This is V1, right? Equals to R in divided by R in plus Rm times Vm, right? Just voltage divider. So you cannot get all the voltage from the previous stage. Then that is a failure because you cannot, the signal get diminished. You cannot amplify as much as you want, right? So what is the ideal situation that you can get all the voltage, even though you have output impedance from the previous stage? How can you, it's just like if the teacher is lousy, how can you make sure that you can learn all the knowledge from that teacher? R in, think carefully, almost. If R in equal to 0, what you get? Oh, Rm. But Rm is your teachers, not you, right? You are the one, right? Now you are the input impedance, right? So almost very good. So you want R in equals to infinite, right? Then you have V1 equal to Vm. Just like if you work really hard, you are a good student, even your teacher is lousy, you can learn all the knowledge. Right? So that's why we hope that the input impedance of any stage a voltage amplifier needs to be infinite, right? Then I don't care about what happened to the previous stage. Similarly, if I want to deliver a voltage to the next stage using the same token, let's say my student doesn't study. How can I make sure they all learn the stuff? I need to make sure my output impedance, this is my output impedance, equals to 0 this time, right? Then the next stage will get exactly what I want. Okay? It's just like if I'm really good teacher, even you don't study, I can teach you everything that I want you to teach. Okay? But as a circuit designer, as a company, you have a product. You don't know who is going to use your product and what you are going to drive and what you're going to get, what signal you're going to get. That's why you want to make your input impedance high, output impedance small, so that you can use in every situation. So more customer can use your product. Okay? Now, why do I want to talk about this? This is related to the definition of the input and output impedance. If I want to find the input impedance of a circuit, naturally, I will just apply the input voltage and then measure the input current, right? Just like a resistor. Apply the input voltage, measure the input current. But however, it also depends what this circuit has, what load this circuit has. Maybe this circuit is driving another stage. Then in that case, you will get different results. So when we use the ideal case, we say that in the case that I out equal to 0, which means it has the loading has the input impedance equals to infinity. So if this is confusing, let me say one more time. Input impedance is defined as V in divided by I in when I out is 0. That is the definition. You accept it. And I try to explain to you why we want to have this definition. First of all, V in divided by I in, of course, is the impedance, right? By definition, right? Very naturally. But why do I want to have an open circuit for its load? Because as I just discussed, we hope that ideally the subsequent stage has an ideal loading, which means it has an infinite input impedance. We are hoping the next stage has infinite impedance, right? Because you need to choose one, and that is the best way to choose. So this is just a human definition. And if you actually loading something very lousy, don't have infinite input impedance, the input impedance seen from here is not going to be really useful by this definition. Similarly, how do I find the output impedance? Right? Again, you know that it's very easy. From the output port, I apply Vx and then measure Ix. That is the output impedance. But we will need to short the input impedance. Short the input, V in. The reason is, again, because we expect the previous stage, we have a 0 output impedance. So you look from this direction, you will see short. That's why you need to short it in order to find the output impedance. And that is just a definition. Think about it. I hope you can relate. If not, at least you need to memorize the definition and the condition. This is very important, right? And this goes back to here. When I try to find this RO, I short the input, remember? So if I want to measure the RO of this transistor, I short the VGS. And because this is short, this is open. Okay. Let's try some example. Can you tell me what is the output impedance of this circuit on the left? How do I find the output impedance? Well, just by definition, right? What is the definition of output impedance we just said? Very good. R out equals to V out divided by I out when V in equals to 0. And what is V in? This one. VGS equal to 0. Because this is 0, so VGS equal to 0, this is open circuit, right? You basically don't need to do any Ohm's law. Just look at here. You just ask anyone who knows resistor. What is the resistor when I look into this resistor? Of course, it's the resistance of that resistor, right? Very straightforward. So R out is R0. Yeah? But if you did not understand this, you are going to run into a lot of trouble. After one page of definition is still wrong because you don't know what is V in. So I see in many midterms before some students not able to do this, and then they have a very long derivation, right? So be careful of this. What is the output impedance when I look up to the source? What is the output impedance? Difficult. All you need to do is just sit down and calculate. Again, definition. But I want to do this. I should first say, what is the transistor type? NMOS, right? And because of this, this is drain, this is source, this is gate. And after that, we draw the small signal model. This is gate. This is drain, this is source. I have this one coming from my cheat sheet. Right? I just replace this 3 terminal with this. And then start to ask, what is the drain? Drain connected to VDD, so it's grounded, right? Source is where I want to test, apply a Vx and measure the Ix. And then the gate, I should throw it, but because of the definition, R out equals to Vx divided by Ix when V in equal to 0. So this one forced me to make Vg equal to 0. Right, so everything has a reason. This is 0 because it is small signal and it is VDD. This is 0 because that is the definition when you need to find the R out. With this, then you can start playing with the KCL, KVL, right? So I'm going to use KCL. What is that? Ix, of course, equal to negative GM V1. This current goes in, must be equal to negative this current, right? They go to the same direction. Some of you may like to say Ix plus GM V1 equal to 0. It's the same. KCL. Is this KCL okay? Then you start doing substitution. Ix is what I want because eventually I need Ix in the R out. But what is V1? Now that is very dangerous. Someone says 0. Be very careful. V1 meaning plus minus V1. So it is what minus what? Vg minus Vs, right? But what is Vg? 0. What is Vs? In terms of the quantity we want, Vx. Right? All I want is just to bring it to Ix and Vx, then I can get R out, right? So clearly Ix equals to GM Vx. So R out equals to Vx divided by Ix equals to 1 over GM. Can it be GM? Can R out equal to GM?
No, if GM is 1.
If GM is 1, can R out be equal to GM still? Yeah, I mean, just in your derivation, right? Maybe I did not do it well. I say R out equal to GM. You should know immediately whether this is right or wrong.
The units are different.
Exactly. The units is different. If I was careless, I say R out equal to GM, then I should know, no, that's wrong. Because This is ohm. Gm is transconductance. It must be 1F, 1 over transconductance. Right? You can come up with 1 over 2 Gm, 1 over Gm plus something. Fine. Then you don't know whether you did it wrong or not. Right? But obviously, if I say RL equal to Gm, I know I'm wrong. This is something you need to check in your derivation. But anyway, the point is this. This is usually small, the Gm. 1 over Gm is small. Okay, and I forgot to say that this is usually large. RL. Okay? So we actually have spent time to understand for a single transistor. When I look into the gate, the impedance is infinity, really large, because it's the gate for DC, right? When I look into the drain, it's pretty large. Not very large, but pretty large. And when I do this, I need to make sure that it is only true if the gate is grounded. If it's not grounded, if it has a signal, this is not R0. And if I look into the source, it is pretty small, 1 over Gm. I don't think you need to memorize this. And this too is not difficult, just two quantity, R out and 1 over Gm, right? As people who have studied analog circuit. These are the two quantity you should be very familiar with, Gm and R out. And because we are talking about resistance, of course it's 1 over Gm, cannot be Gm, right? Looking from top R out, looking from bottom 1 over Gm, large and small. Is that clear? Let's just go through some example to see, has a final summary on the DC biasing and AC signal. This is an amplifier, but based on all what we have learned, this is the speaker, right? It comes up with some small signal, maybe 10 millivolts, right? I speak, and then the microphone convert to electrical signal, we try to amplify. Is this going to work, this circuit? Does it work? This is the full circuit. This is not a small signal circuit. Yeah, there's no DC biasing. What you're giving to this gate is either negative 10 millivolt or plus 10 millivolt, right? The transistor is always off because there's no gate biasing. You need to bias the gate to saturation. I hope this is obvious to you now. So you do not just say, oh, get this circuit, let me draw the small signal model, and then say, I do get the gain. No, because you cannot draw the small signal model. It's not DC biased correctly. It's not even in on state. There's no that you cannot draw this circuit. This is only true because you put it in the saturation, right? How about this one? So we follow your suggestion. I have a DC bias, and then I connect to this microphone. Is it going to work? No. Why? Very good. Yeah, because it's a constant. VGS equals to 2.5 volt. Yeah, you may say, yeah, isn't that I connect it to here? But this is, we assume this is so strong. This is a DC. You have a very strong power source. Just keep this point at 2.5. Then what will happen? Your microphone is just not working. You have a constant current or constant voltage applied to the output. The whole thing is failing. Okay? So what can we do? Then someone came up with this. And it should work now, right? Just based on the drama. Eventually it should, the plot, right? So this may be, we pass in 1.5 volt. And then you do this series, VGS, right? So the total VGS equal to VGS plus 1.5 volts. And this is the DC part. Now you can make this into small signal and amplify it. Is that okay? Right? Basically, this is what I've been saying. You DC bias it, and then you apply the small signal on top of it. And this is going to amplify this small signal. Yeah. Any questions? A pretty good timing today. A little bit rushed, but we can review more if you have questions. Right? So we are done with this